This one's A, B, and D. Because this one's a double bond on carbonic double C double bond.
This was a 7 from bottom.
It's a carboxylic acid, but it has a carbonyl group. A carbonyl group is just this.
Okay, so let's go ahead and get started. I'm gonna call someone and we'll go over the answers and then we'll get to today's. Like I said, I had every intention of giving you flashcards today, but Amazon has failed me. So you should be getting flashcards on Friday to start working on. But we are starting reactions today. I looked at what I've done in prior years and we may not get through everything here, but I left all the slides in here. Whatever we don't finish, we'll get to on Friday. There is a lot of work with a specific mechanism. So we'll be actually going back over mechanisms today. Yay. All right. So today we're going to be doing, like you can see up there, well, that was the schedule I had before I was sick on Monday. I didn't mean to be missing on Monday. Thanks, stomach flu. But we're only going to be behind a day. We should be fine because we're actually still ahead of where I was last year with the A-level class. So believe it or not, this is the last unit of study. I believe there are 6 or 7 parts here. So we will be finishing right before spring break is where we'll likely be. And so I'll reveal more information to you on Friday, but we are today starting with reactions. And so you might be seeing some quizzes coming up starting next week to practice on memorizing your organic reactions. So I'll work more on that structure and strategy and reveal that to you either probably this Friday if possible. All right, so let's go ahead and get started. Period. I think everybody got checked so far. Let's find out. Has a 6 out of 10, but we'll double check now. This is for Diane.
I don't bother anymore.
You know, the one day that you don't
It's the one day it's gonna call me. That's why I didn't do it.
8. All right, round of applause. That's your first mark on round 4. Remember, at the completion of round 4, you do get pizza at the end of the year. So you are 11 more Beller points away from that. And we have not started quarter 4, so we are on track. Your class is on track to get pizza, hopefully, if you keep doing well. The only class I'm worried about right now is period 2 at the moment, because they have to earn 7 plus 12. They have to earn 19 more points in order to get the pizza. All right. So, like I said, I will have your donuts for you at the end of class today. After the conclusion of the lesson, wherever we're at 9:15, we'll go ahead and we'll cut it at that point. So let's go ahead and get started with the bell work review. Let me make sure real quick though that I have attendance submitted. Okay. All right, so not everybody got the first point. Most of you did very well in this table, like got most of the points in this table. This first point here, carbonyl groups. You should write this out because a lot of people get confused between carbonyl and carboxyl. Carbonyl groups are only aldehydes and ketones. Carbonyl groups are aldehydes and ketones only. When you add the oxygen, the second oxygen, it's no longer called a carbonyl group, it's called a carboxyl group. So carboxylic acids are part of something called a carboxyl group, not a carbonyl group, which is why they're called carboxyl salts, carbokxylate salts when you put them as ONA. So you should write that little note for yourself. I'm going to put a couple more little notes on here because these wordings is what's going to mess you up on a paper 4 is really, are they talking about carbonyls? Are they talking about carboxyls? What's the difference? So carbonyl is, and by the way, this is actually paper 2, but some of these topics can show up on paper 4. So I wanted to review. So the answer here would then be what? A and B only. And you had to get them both right with no incorrect answers in order to get this correct. A is a ketone, bless you, and B is an aldehyde. C is an alcohol, that's what we're identifying, right? And then D is a carboxylic acid. You do have to know your functional groups, which is why I gave practice when I wasn't here on functional groups, because that's one thing that's like absolutely non-negotiable, because how things react depends on what functional group you have. All right, tolerance reagent. That was the silver mirror. So I think you all got that you get a silver mirror from that. And the compounds identified specifically with tolerance reagents, only aldehydes. Only aldehydes. So once you've identified what your aldehyde is, you know your answer must be what? Alkaline solution of iodine. That is actually the I2OH minus thing. And that will give you a yellow precipitate, which I saw many of you got that part right, yellow PPT. The identity of that precipitate is CHI3. You don't have to write that in here, that's not part of the marks, but it's actually important to understand why. The answer is what it is. CHI3 is only produced with methyl ketones or methyl alcohols. It has to be a methyl group because one of the carbons, the methyl carbon, breaks off to make the yellow precipitate. So this is a methyl alcohol because it has a carbon next to the carbon that has the OH. That's the methyl of the methyl alcohol that they're talking about. And then this right here is a methyl ketone because that right there is the CH3 that would break off. So one carbon breaks off in that specific reaction. And that's why that's the precipitate you get. So the answers here are A and C. And they gave up points. The way that they gave the marks was they gave a mark for that, a mark for that, a mark for that, a mark for that. That paper too was so kind. Like every single one you got was a mark. And then sodium metal. You remember what sodium metal reacts with? Carboxylic acids is one of them. But it also reacts with alcohols. It gives you ONA in both of them. So here we would get that the answers are C and D. 1 point for each. And then here's where I said to a few of you that you may not have gotten the mark if you said hydrogen gas produced, because you don't observe that it's hydrogen. How do you know? It looks the same as every other gas. So what's the observation when a reaction occurs that they give you the point for it? Observation, remember, is what do you see? Wow, well, that's bigger than that. But anyways, what do you see? What you should see is fizzing or bubbling. That's the answer they were looking for. Or effervescence, if you want to say effervescence. Fizzing, bubbling, effervescence. One of those three is the one I would say. Yes, it's hydrogen gas that's being produced because you know the reaction, but they're asking what do you see? And because it's taking place in solution, you should see bubbling. You should see fizzing. The gas itself is colorless. Hydrogen gas doesn't have a color, so how do you say it? Do you see the hydrogen atoms? You don't. So that's what you have to be very careful with when you're answering observation is, I'm doing this lab, what do I see? I see fizzing. And then if we wanted to check that it's hydrogen gas, we could light a wood splint and it would pop in a test tube. We'll go up. You remember that little pop? That's the one that we did. All right, so that was a lot of points from a paper two. I had mentioned last year, if chemical tests show up on paper two, they can show up heavy, meaning that this was like almost 20% of their paper two. I know some of you are sad that this wasn't 20% of your paper two if you liked organic. It was a love-hate relationship. Some people love it, some people hate it. But there's a non-zero chance that this also shows up on this year's test on paper four. So that's why I want to go back to review some of the older topics because they can show up. Because remember, this is like one book, all of it's together. Most of what's assessed on paper four is from what we learned this year, but there will be some things from AS chemistry in there. Okay, this one everybody got right. Yay! It was an addition reaction. Everybody that I read, at least, everybody that had me check got this correct. Some of you were even fancier and you specified that it was electrophilic addition, which you might have gotten because I had it right here, but maybe you got it on your own. It is electrophilic addition. So before moving on, we're going to go over the objectives now. Remember, I am recording the lesson today, and I will be posting it on YouTube and then sharing it out with everyone. The homework. Depending on how far we get today, you may not receive the homework today. You may receive it on Friday because the homework includes mechanisms, and I'm not sure how far into today's lesson we're going to get based on what I did last year. And look, it's a lot. When there's a lot of standards, that means that not any of them are super difficult, but you are going to want to pay careful attention because organic is organic. Organic is one of those things that, for me, was the easiest chemistry to comprehend. Like, I understood it, but the easiest to go back out unless you were constantly revisiting and reviewing it. So that's why you are encouraged to start working on flashcards. If you want to wait till Friday, that's fine, because I have some coming for you. But if you have flashcards, you want to start working on writing them out as we're going through the lesson, please feel free. All right, so we got a lot of stuff to do today. We're going to be talking about substitution reactions and how they happen. We're going to talk about nitration, so how you get those NO2s. You're totally not going to be told exactly how to make TNT, but with the information here, you'll actually know how to nitrate and add methyl groups. Use that information wisely, not unwisely. What?
Is it like
I believe probably. Yeah, look at the legality of that. We'll be learning how to add carbons into benzenes. We'll be learning how to add halogens into benzenes. We'll be learning how to add all the things into benzenes, and it's all with the same mechanism. Then we're going to learn about how to oxidize the side chain. Hot KMNO4 is coming back. I know, your friends from last year. And then dilute acid to give benzoic acid. We're going to be talking about hydrogenation to give a cyclohexane. And then we're going to spend time, if we have the time, on the mechanism today, on how all the substitutions happen. So it's going to be a long day. We got a big lesson to cover. And like I said, whatever we don't get done today, we will get done on Friday. And then at 9:15, we'll stop and you'll get your reward for all your hard work during the small hours. All right, so let's go ahead and get started. Electrophilic addition mechanism. This is a mechanism from last year, but I wanted to compare and contrast this to the mechanism we're going to learn today. So I want you to take a moment with a pencil and see if you remember how to do this mechanism. There are 4 marks here. See if you can earn any of those marks. I'm going to give you a couple of minutes to try it before we get started.
Yeah, it's illegal.
What?
it's illegal?
What's illegal? It is illegal. I figured it was illegal.
Like I did tonight.
But like if I don't use it, it's just like,
So we're 6 months.
it's like, what's it called? It's like bandwidth. Or if I have a fire, somebody finds out, well then, maybe they'll recruit to the FBI. Like, hear me out, right? How am I gonna forget to leave, like, how am I gonna forget to turn off the stove if I have literal dynamite in my house? Like,
But I feel like you would still learn.
It's all about the.
it's like double.
Like, do be careful with the over the school then.
Yeah, I could.
Oh, I'm there.
You were on the school Wi-Fi?
Maybe.
My phone auto connects to it.
No, I wasn't. It's in my other stuff. That doesn't
Just say you were in chemistry class. Had a question.
Documented here because we did the part in the H.
Wait, class teaches us how to do a lot of things.
I
Because Cambridge, that's a.
Yeah. Like, I think Jorge was telling me that, like, if we really wanted to, we have enough knowledge to make most turns.
Yeah.
Use your knowledge for wise purposes, not unwise purposes.
I wouldn't. Never. Picture.
It's not that clean.
I don't know what a pharmacist does, so that's a.
What?
Right.
Did you say that?
We could follow that.
You should make
Pharmacist
a
does
non-medical
medicine. Why did you start the next?
What?
You could do a acid, like an aspect transformation.
Into what? Wait, aspirin is what?
You would have to know what aspirin is and figure it out. Or like you gotta tell you how to make the drugs.
Not the half arrows. Half arrows are for homolytic fission, which is only free radical substitution.
Yeah.
You have to use full arrows.
That's what you do it. How'd you do it?
I haven't done it yet. Yeah.
So start with the dipoles as a clue. Start with the dipoles as a clue. Do you remember dipoles?
I don't remember how to do it. Right. Oh, bro.
One of the dipoles.
I don't know. Leave me alone.
I don't know what to do.
I will be going over it.
I have an empty.
The guy plays.
You remember.
It's
so
actually
weird.
fucking here.
Just show that bromine is one electromagnetic effect.
No, that's
Show that yes, the electrons are so big. And then it'll go.
This is so wrong.
And then it'll.
Uh-oh.
I don't get it.
So then
Probably
you get
great.
All right, I'll go over it in a minute.
You like
Is this the one where carbon?
Like theoretically, I know what to do, but do I remember like the arrows and the half arrows? And
That's what we have to remember.
telling me, oh no, like, okay.
I just know double half arrows. And then
I think you guys did really good mental mechanism on do last year.
I thank the Lord.
Hopes and prayers. I'm gonna put this H.
Was it those organic, what's his mechanisms? I just
Oh no, it's
Fail.
It's just
It failed.
Oh, but I only gave one with a mechanism. You just remember that one multiple times?
I guess.
I gave most of them with just reactions.
Well then, I just not good at organic guys. Because I think my highest grade on one of those was like a 75.
I know I did well on the first
It's-
quiz.
It's my best bet.
And then after
I
that,
mean, it does. It makes sense. Yeah. Like,
The 75 was like the last one, and the only reason why is because I had remembered which ones I've gotten wrong previously.
Okay, wait. Okay, maybe we.
Not because I remembered that it is actually that.
Multiple arrows.
Like if that makes sense.
Well, like,
right.
You were the best.
You're wrong.
so let's go over it.
thought wasn't.
Let me get your full attention so I can remind you on how it works. Because the mechanism we have today is also going to be electrophilic. But it's not going to be electrophilic addition, it's going to be electrophilic substitution. So with this mechanism, how you start it is you have to write dipoles where there should be dipoles. This molecule right here is nonpolar. So don't write dipoles on your organic molecule. Write your dipoles on HBr. Do you remember of hydrogen and bromine, what should have the negative charge? The halogen always. So even if you don't know the numbers, the halogen should have the partial negative charge, and the hydrogen should have the partial positive charge. So far, so good? All right, this is your beginning. The beginning of this reaction, the thing to remember about mechanisms is that curly arrows, and I wrote this for AS recently too, always start at pairs of electrons and end at positive charges. Because negatives are attracted to positives. That's that main idea. So you may want to write that down. Because once you have this dipole, where do you think the pair of electrons is going to be coming from that's looking for a positive charge? If you don't remember, it's okay. Pi bond. The first thing that happens is this pi bond is an extra pair of electrons. That bond breaks. It grabs, those two electrons grab the hydrogen. Why do they grab the hydrogen? Because electrons are negative and hydrogen is positive. But hydrogen can make how many bonds? So these two electrons swing out, grab hydrogen as a chemical bond. Hydrogen can make how many bonds? One. So hydrogen cannot be connected to carbon and also be connected to bromine. So what else has to happen? This bond right here has to break, and those two electrons have to go to bromine. And so your first mark here, mark 1, is for your dipoles on HBr and the curly arrows in step 1. Mark 2 is your intermediate. What would my intermediate be? If you remember Markovnikov's rule, you're like, oh. Markovnikov? This is an uneven adding. The hydrogen should go to the side of the molecule that has the most hydrogens. Because the carbocation is most stabilized when it has more carbon groups. We call this the inductive effect. So then what I get here, I'm going to rewrite this. H3C, C, CH3. This is not a double bond anymore. It's a single bond, CHH. And then my question to you is, where does this hydrogen add to? The left-hand carbon or the right-hand carbon? Because this is the stable, more stable cation. So I'm writing the reason. Due to the inductive effect of these methyl groups, they stabilize that cation, whereas this carbon right here has nothing to help it. Hydrogens are very unhelpful. They don't have electron cloud density to build me. Does this kind of ring a bell? Yes. Okay, so Mark 2 is for that correct intermediate. So we got that. Mark 3, actually this is 4 marks, so they gave you 2 marks in here. 1 for the dipoles, 1 for the curly arrows. The next mark would be, well, what else has to add? Bromine. And so you write your bromine again. At minimum, you must write 2 electrons on the bromine. I don't like doing that because I like to write it with all of its valence electrons. But for Cambridge, they would accept if you did it like this, where these 2 electrons are the 2 that are coming from that bond. I'm a completionist, so like that's how it exists. But if you wrote 2, that's fine. And then you have to do a curly arrow from this pair of electrons to the carbon. Remember, curly arrows always start at a pair of electrons and end at a positive charge. And so this would be a mark right there to do that. And then they already gave you the product, so you don't need that. It says the structure of 2-bromo, 2-methylpropane. And they told you that they wanted the bromine on carbon 2 on top of that. And they told you where to add to, technically in the question. And so mark 3, this is actually marks 1 and 2. Mark 3 would be the final curly arrow to add Br minus. All right, does this idea ring a bell now? The mechanisms. Remember that you're always starting from a pair of electrons to a positive charge. All the mechanisms that we do this year, which there's only 2. By the way, last year we had 5 mechanisms to learn. In A level, there's only 2. The one that we learned today or next class is big though, meaning that it's only 1 mechanism, but it has like 4 or 5 different ways it could show up. So it's only 2 mechanisms, but it shows up in many different ways. So we're ready to go over new stuff. This was actually all review. Up until this point, we haven't looked at anything new for A level. Let's go over, what does benzene do? Yay! First thing benzene can do. If you recall from last class, benzene does not exactly react like alkenes. So you may want to write that for yourself. Benzene does not exactly react like alkenes. So it doesn't do the reactions that alkenes do in the same way, traditionally, because its electrons are not localized. They're delocalized, meaning that this isn't 3 separate alkenes. It's really supposed to be thought of as a ring, like that. So because of that, you will not be able to add bromine the same way that you could to an alkene. In an alkene, you could add bromine to each side of the double bond. No conditions needed. It would just happen. Benzene doesn't do that. The first thing benzene does is this, and you should write this down. This would be your first flashcard. You can substitute a bromine or a chlorine into the benzene ring in the place of hydrogen. So maybe write that hydrogen out so you see what's actually happening. A hydrogen will actually be leaving and a bromine will be taking its place. This is called a substitution reaction because one thing is leaving and one thing is going in. What you need for this, there are specific conditions, is you need an FeBr3 catalyst or an AlBr3 catalyst. You can also do this reaction with chlorine instead of bromine. Do I have a second slide? I do have a second slide. But you can also do this reaction with chlorine instead of bromine. It's the same conditions. The type of reaction is called electrophilic substitution. That will make more sense once we learn the mechanism. And then this part about methylbenzene, we'll look at this later once we look at inductive effects a little bit more. So for now, you just need to remember, if you see this, what would you make? This is an example reaction. Replace a hydrogen. Does it matter which hydrogen you replace? It does not. HBr. The byproduct would be HBr. Does it matter? No. So if you want to place it down there, feel free. If you want to place it over here, feel free. If you want to place the bromine up there, feel free. It does not matter. And then yes, there would be a byproduct of an HBr. HBr byproduct. Remember that in this course, typically we only ask you for the major organic products, but you know, you could be asked for a byproduct, so I'm not leaving it for you. And we'll see it in the mechanism. We'll see the byproduct show up. All right, so that's the first one. Br2, and you need a catalyst of FeBr3. This catalyst is actually really important. And when we see the mechanism, we'll see why it's important. The next reaction is almost exactly the same. I wrote it as reaction number 2, but if you pay attention, it's the same thing. If you look at the next one, it says substitution with chlorine. So instead of bromine, we use chlorine. So that means the catalyst would be the same thing, but instead of FeBr3 or AlBr3, we would use a catalyst of FeCl3 or AlCl3. It's still electrophilic substitution, and then later on, we'll talk about this. Again, that part at the bottom, we'll get to. You only need to include the catalyst. You don't have to include everything that's on this picture. I got this from online, but for Cambridge, the main thing that you must include is that catalyst. That's what they're looking for. So what would this look like? Plus Cl2 over, let's do FeCl3. And our product here would be what? Place a chlorine anywhere, doesn't matter. And what would your byproduct be? Let's see what that's HCl. So actually very similar to other substitution reactions we saw back in AS Chem. But the key difference here is that benzene, this is not an addition reaction. 2 chlorines are not adding across the double bond because benzene double bonds are not like regular alkene double bonds. So it's that something else is happening that we'll be looking at a little bit later in more great detail. For now, you just have to know this happens. All right, so halogen, got the catalyst, substitution. Hydrogen gets out, halogen goes in. That's it. Those were our first 2 reactions. And they're the same as each other. And actually, most of these substitutions will be the same as each other. They will be very similar. Hydrogen's getting out, something's going in. The next one is something special. So in the next reaction, so you do need to have, every reaction I bring up is one you are going to need to have on a flashcard for yourself to remember. And like I said, on Friday, I will let you know when you're going to have quizzes to practice this. And yes, the quizzes will be graded. Expected to possibly be next week. Or starting next week.
Like quizzes?
Like QUIZZES, not the digital thing, but actual quizzes. Yes, like 10 question quizzes, like mini assessments, like it was last year. Yeah, it'll be less of them though, because there's less content. UV light. So if there's UV light, you get something called a free radical substitution. Do you remember that thing?
Yeah.
Of the side chain. Yeah, I was
Oh
like,
my God,
yes.
yeah.
So what happens in this case is instead of the chlorine taking the spot of a hydrogen on the benzene ring, the chlorine will take the spot of a hydrogen where? If I have UV light. What do you think your product might be? Just remember what regular free radical substitution was from the past. Just to remind you, like what it was in AS Chem. If I had this, I would get CH3Cl and HCl. A hydrogen would swap for a halogen. So what happens here? What do you think?
Sulfur.
On the methyl group, not on the benzene ring. So if I've got UV light, you get this. And I'm going to continue using the circle instead of the 3 double bonds just to show that these are delocalized electrons. So you would get CH2Cl. And the byproduct would be HCl. So the thing you have to remember here is if you have a side chain and you have UV light, the chlorine doesn't go to the benzene ring. The chlorine goes to the side chain. The chlorine can't go to the benzene ring. Why not? Is the condition met for the substitution to go into the benzene ring? No, because you don't have the catalyst. Like, this cannot, this, I'm just going to bring it up here. This is not ever going to be the answer. Why not? Why won't that be the answer? In order for the substitution to happen, you have to have catalyst. No catalyst, no substitution into the benzene ring. So this is not going to happen. This is an example of something that's no reaction. Well, not no reaction, but this doesn't happen. What? This chlorine cannot add here. It adds to, like, it substitutes at the top, not in the benzene ring. Does that kind of make sense? Because the condition for into the benzene ring is not there. It has to have this to go to the benzene ring. So be careful with that. It's a type of question that can show up that could mess you up. So what if I had this? What would this be? The catalyst is either AlCl3, right? So what would this answer be? Just to give you another example, so you can see the idea. Where would the bromine go? And it actually doesn't matter. It can go either to swap out one of these hydrogens or one of these hydrogens, right? It doesn't. So you could get CH2, CH2Br, and you could get CHBr, CH3. You may recall that in a free radical substitution, it's not targeted, meaning that when a propagation happens, this happens over and over and over and over again. It could attack equally any of the hydrogens that are there on that side chain, meaning that it could attack the end or it could attack the middle when you have a free radical substitution. So this gives you a mixture of products. So this is not a good technique for making something you want because you're going to get more than one product out of this. You could actually get more products too. But do you see the difference? This cannot go on the benzene ring. Why can the bromine not go on the benzene ring and swap from one of the hydrogens on the benzene ring? You don't have the catalyst, AlBr3 or FeBr3. You have to have a catalyst to get the substitution on the benzene ring. The difference is, what? What happened? So free radical substitution must happen with the side chain, not the benzene ring. All right, so the next one. And I told you there's a lot of benzene reactions. We're getting through a lot of them today. The next one's called nitration. So go ahead and write this one down. This one should be on a flashcard. If you're taking notes on separate paper, you should write it. Nitration of benzene. This is how you get NO2 on a benzene ring. If you think about the conditions, this is actually wild. What you need in order to make this happen is a mixture of concentrated nitric acid, concentrated sulfuric acid, and 55 degrees Celsius is like 140, 150 degrees Fahrenheit. So hot, concentrated acids. Hot, concentrated, very dangerous acids. You mix that all together and you can nitrate a benzene. I wonder why TNT, the production of TNT could be dangerous. Because remember, we said TNT has those nitro groups on it. So this is actually kind of a dangerous reaction to run. I would not run this in a backyard. I would not run this in my lab either.
I mean, TBH, when you say HCl.
HCl, muriatic acid.
How is it more dangerous?
The thing is, muriatic acid, that your pool has tons of water. So like it dilutes the acid a lot. So you're not actually, like you have stomach acid too, and you're not dying from that. Yeah. All right, so what happens here with this mixture? You get NO2 on a benzene ring. And does it matter where the NO2 goes? No, once again, it goes anywhere. Is it gonna matter eventually where it goes if I have more than one thing on a benzene ring? Yes, that's when it's gonna get a little bit more complicated and we will address that today. But for now, you just have to know this. For now. But you also do have to memorize the condition. So remember when you do a flashcard, you have to do your general reaction. You also need to do your conditions. I'll remind you on Friday when I have the flashcards. Yes. So you'll see it later on. The byproduct, I think I have it in here. It's all of this. That'll come later on. Maybe not even today. See, we still got a lot to get through. All right, so we are now ready to talk about something really important. Remember this thing I said, comparison. I kept saying later. We're now going to start talking about what I said I was going to save for later. Electron donating and electron withdrawing groups. So this is a really important topic that I need your full attention for. If there is already, so this, if there is already a group on benzene, it will direct other groups being added. So you're going to want to write this down. If there is already a substituent or a group that's on a benzene ring, it will direct any other groups that are being added. It's kind of like I got here first. You're going to go right there. You're going to go right there. So this CH3 is bossing everything else around. That's going to come on and it's like, you go here, you go there, you go there. So if any of you have great leadership qualities, you know what that's like when you direct. So we call the electron donating groups and electron withdrawing groups, we call them directors, directing groups. And so an electron donating group is a group that's present on the benzene ring that donates electrons. We've heard this idea before because we heard it when we heard about the inductive effect. You remember the inductive effect back in AS chemistry? Inductive effect was when methyl groups, like carbon groups, donated to stabilize whatever group I had. And in that case, it was a carbocation. Here it's going to be we've stabilized the benzene ring. So CH3, what it does is it donates electrons to stabilize the ring. And it activates certain positions. So electron donating groups activate, and yes, the word used is activate, the 2, 4, and 6 positions on a benzene ring. What is a 2, 4, and 6 position? 2, 4, and 6 from where? Where would carbon 1 be? Carbon 1's going to be at the top, wherever that group is. So this would be carbon 1. It would activate positions 2, 4, and 6. What do I mean by that? I'm going to switch colors here. Any groups being substituted into this ring would only be able to be substituted into positions 2, 4, and 6 if there's an electron donating group there. You may want to do colors for that or highlight. As of the 2022 standards and included in the 2025, you are, so I guess this is bad news. You are being asked to remember the electron donating groups by heart. Meaning amines, alcohols, ethers, amides, methyl groups, longer methyl groups, right? More carbons. Alkyl means carbons and chlorine. All donate electrons into the ring. So you should highlight that. They do want you to know that. I'm going to give you my reasoning. To me, amines and alcohols are very similar. They both have an unshared pair of electrons. Here's 2 that can be donated into the ring. Here, I also have that same situation. So amines, alcohols, ethers kind of have a similar situation going on. Here are the nitrogens. This is attached to the nitrogen. So that's also got a pair of electrons to donate in. I already knew about all the carbon groups because of the inductive effect that they always donate electrons in. And then chlorine has pairs of electrons that could be donated in. So that's part of my reasoning. I'll give you my reasoning on electron drawing groups as well, like what worked for me to help remember them. So I remember always if I see carbon chains, if I see alcohols and amines, those are going to be donating groups and will cause other groups to be added to 2, 4, 6. So what does that mean in an example question? What would an example question look like here? Let's say I had this, and I had, let's say, OH. Yeah, phenol. Actually, I don't want to do phenol yet, because phenol has its own lessons. Phenol has its own thing. So let's do this. If I have this, and I have this, where are the 3 possibilities where this bromine can be added? Technically, it's only 2. Because it's symmetrical. So the 2 and 6 positions are the same. So what are the 2 places I can put this bromine? Where does the CH3 direct bromine to? It has to either go here or at the bottom. So your 2 answers, and you would make an equivalent amount of each, would be this, and what would the other one be? Where would I put the bromine for the second one? Put it at the bottom. 2, 4, and or 6 positions. Why do I not include writing the position 6? Position 6 is position 2. Like it's the one that's just one away. Like if I had wrote this, that's the same thing because it's just like if I go counterclockwise, that's the same thing as that. I do not need to write this. Unnecessary. Did it? All right, so I'm going to pause a little bit, give you some time, and then we'll continue with electron withdrawing groups. The electron donating groups, their main idea is they donate electrons into the ring. They activate the ring in specific positions, those positions being 2, 4, and 6. Electron withdrawing groups are going to take away electron density from the ring. They're going to destabilize the ring and activate different positions. Ready? All right. I don't know. You may want to take a picture real quick. There's a lot here. Do you want to? All right. So electron withdrawing. Oh, sorry. Go ahead. And we'll see more examples in a little bit. I just want to show you as I'm talking about it as well. So electron withdrawing groups, the opposite things happen with electron withdrawing groups. Electron withdrawing groups are groups that are present attached to a benzene ring already, that instead of putting electrons into the ring, they take electrons out from the ring. So withdraw electrons from the benzene ring. I always think of them as destabilizers. They destabilize the benzene ring. And so they activate different positions, the 3 and 5 positions. So I remember that with donating is 2, 4, 6 and withdrawing is 3, 5. And so what does this look like? Why is this the way that it is? Let's take a look at some of them. We're going to take a look at aldehyde. This is a withdrawing group because this electronegative oxygen, the way that it's organized, is actually the same reason that aldehydes and carboxylic acids are very far down on the deshielding in terms of their spectra. This actually pulls electrons up towards the oxygen, pulls electrons away. And it makes even more sense when you look at it with a carboxylic acid, because with a carboxylic acid, that's definitely pulling electrons up toward it. It's not donating electrons in because of all those electronegative oxygens, it's pulling them up. And so that's a destabilizer. Notice that ester is actually very similar to that structure. And ester, which is this, also has a very similar structure. And it's pulling electrons up out of the ring, not donating them in. And so I would definitely know these. And then cyanide does the same thing, NO2 and NH3+.
Please pardon this interruption. Again, students, if you have a school-issued device, I need you to turn it on and log in at this time. Again, if you have a school-issued device, I need you to log in right now. Thank you.
Updates. Let's talk about NH3+ real quick. Why would that be taking away electrons from the ring? Taking a look at NH3+. Because it says NH3+ is on top. Do we have any justification of why? Because when we had NH2 in the last one, we said NH2 was donating a lot of electrons into the ring. But NH3+ is taking them away. Why? There's no unshared pair here. And nitrogen is very negative. So that's what pulls the electrons up out of the ring. Does that kind of make sense? So the common theme here is you've got very electronegative groups that are pulling electrons out from the ring, and you don't have unshared pairs of electrons right next to the benzene ring to donate it. Kind of make sense? So that's what's going on with the electron withdrawing group. So if I have one of these guys present, it means that any group that's going to be added now is going to be added to position 3 or 5. And so let's take a look. Let's do, I don't know, benzoic acid. That's a common one from Cambridge. Benzoic acid, we're going to add, let's do this one. Cr2, FeBr3. Where would the bromine add? So we said it's the 3 and 5. So this is 1. This would be 3. Are we good with that? This would be 5. Would you agree with me? 3 and 5 are the same. So technically, I do not need to write 2 products. I only need to write 1. So it is the identity of the group that's already existing on the benzene ring that tells us what to do. That directing group tells us what to do, where to add additional groups. That's a big idea that I need to practice that today. We'll do practice questions in a little bit. Yes.
So for the electron, like the adding one, it has two at the end, and then it goes from the brown group, there's no one.
The products?
Yeah.
You have equivalent amounts of two different products here. And here there's only one different product. That's correct. Because like if I wrote this, it would be like why? There's no reason to write this. Because this is carbon group. Like three this way is the same as 3 that way.
Okay.
So that's why I don't include a second product here. Even though technically it adds 3 or 5, 3 and 5 are the same. So it's basically adding to the same position 2 or 1.
So one on the questions you use like the other one you put two.
Exactly. We will practice this more, no worries. But I want you to kind of get the idea at least of what's going on before we continue. I know some of you are participating in the chemistry Olympiad tomorrow. So I'm going to take a brief side note to address you. In this topic, in the American curriculum, these places where the groups add have different names, and I'm going to bring them up. So I'm going to keep this. I'm going to add a separate slide. This is important for anybody who's studying Olympiad. So this position right here, which we know is position 2, it's called in American chemistry by American chemists the ortho position.
It's actually one.
You may want to write this. So this is like Olympiad side note, because I know that the Olympiad's happening tomorrow. There's a non-zero chance that this could show. Anything can show. Technically in the Olympiad, anything from chemistry ever can show up. That's how they differentiate the levels, just like Cambridge. So that's an ortho position. Let's do this, COOH. This position right here, the 21208 is called the meta position. That's called the meta position. Yeah, it is. It's called the meta position. And the one that's at the bottom is called the para position. So I remember it as OMP. Ortho is the second, meta is the third, and then para is the fourth. And so they would say it as electron directing groups would go to the para positions, and electron withdrawing groups go to the meta position.
Just say 1, 2, 3.
That's how Cambridge Internationally does it, actually. They just say 1, 2, 3, they just do numbers.
The correct one.
When I memorized for my organic classes, I did not unfortunately learn it that way. I learned it as ortho meta para, actually. So I learned it that way first, and then when I started to Cambridge, I was like, oh, this is so much better. They have their own names. So I'm just giving this for you, so you have it just in case you get an electrophilic substitution reaction. You have what that could also be called. They do sometimes a single letter. The single letter for ortho, what do you think it would be? O. The single letter for meta, M. The single letter for para, P. That's it. So if you see like OMP with a benzene ring, they're talking about ortho meta para. Just side note, linguistics are hard. Language is like the hardest part, like knowing what's going on. Let's see, reading is the hardest part. Practice questions. Let's take a look at some practice questions. I think this is from the text on what we have just been going over. Draw the structures of the products formed in each of these cases. One Cl atom is substituted into C6H5NH2. When you see C6H5, what do you understand that as now? Benzene. Because benzene itself is C6H. What? Benzene itself is what? C6H6. So if I take a group out and replace it with whatever that is, instead of having 6 hydrogens, I'm going to have 5. Does that make sense? So every time I see C6H5, I'm just looking at benzene. So this is benzene with NH2. I want to put chlorine in it. Where does it go? What do I have to analyze to make this prediction? What is NH2 doing? Is it donating or withdrawing? Because of the unshared pair. That's how I reason it. The unshared pair donates, because the unshared pair is right there on the next atom. It donates electrons into the ring, which means it's up. And we just call it EDG, electron donating group, instead of writing all the words. EDG means that where am I putting this fluorine? 2, 4. 2, 4, 6, but like 2 and 6 are the same. So I'm going to put 2 or 4. So I get 2 products. So this would be NH2Cl plus NH2Cl. Good so far? I'll pause because you need to write this down. Make sure to write the benzene ring. In my AS Chem class, they forgot to write the ring yesterday in one of the competitions and lost their points.
Oh yeah. Yeah, your friend Jennifer and Kashayla are like,
Wow.
in first place.
Yeah.
They took a commanding yesterday.
Oh, you're right. Thank you, Rosalind. Should be right there. Thank you. It should be here, and it should be there. 4. Are we good? Yeah, fix it. It should be 2 and 4. 2 and 4. Sorry, fix this. Bring it 2 and 4. The one at the bottom. It should be 2 and 4. Rosalind's absolutely correct. I accidentally wrote up 3. 2 and 4. I'll pause. We have it? 2 and 4. You're working ahead. Okay, so 2 NO2 groups are substituted into methylbenzene, meaning they want you to add 2 NO2 groups on the same methylbenzene. So how would I do that? So first of all, I would want to write that I have excess NO2, which is coming from HNO3, H2SO4, just to remember our conditions. I'm writing the conditions because if you rewrite them, it's going to help you remember them. So you should write the conditions as you're practicing. All right, it said we add 2. Excess meaning 2 NO2s, right? In this case. So you, instead of writing excess, you could just write 2 NO2s. Because if I write excess, it could be 3 NO2s. 2 NO2s. Where do I want them? What are my options? Don't I have multiple options? What are the options? So what are the different answers I could give for 2 NO2 groups on a methylbenzene? 2, 4, and 2, 6. So NO2, and the other option for 2 is 2 and 6. Why not 4 and 6? The same as 2 and 6, right? I mean 2 and 4. 2 and 4 is the same as 6 and 4 because it's symmetrical. Does that make sense? The next one, no? All right, 2Br atoms substituted into C6H5COOH. All righty, this one. What does COOH do? Is that a withdrawer or a donator? So that means we're going 3 and 5, right? We have to put 2 bromine atoms, so it's plus 2Br2. I'm picking a catalyst, doesn't matter which of the 2 I choose. Are there any other options to put 2 bromines on 3 and 5 than to put on 3 and 5? I believe we only have one choice here. We're adding to both positions a bromine here and a bromine there. There's no other options. All right. Okay with this?
Yes.
I know you're all so excited to look at this mechanism today. We're gonna take a look at electrophilic substitution mechanism, but beforehand, we're gonna do a couple more practice questions. So if you have some extra space, let me see. On the back of your handout, we'll do a couple more practice questions just to make sure you're getting the idea. So, practice questions. Remember, when you get practice quizzes, you're gonna get a bunch of practice questions. Let's see. What would you do? What would you do here? It's just one here. Yes. You can see I should go, yes. So what do we get here? Yeah, all potential unique products. You do not have to include a byproduct. Okay, like. Do you get this plus this? Go ahead. Remember, when they're drawn, it's not always going to be drawn at the top. That might be drawn on the side. And you still have to recognize that that's carbon number 1. All right, so that was the first unique scenario I wanted to bring up. What?
Like in products. I just shifted a little.
You can, as long as it's 2 and 4 from the CH3, you can, like, molecules move around. All right, let's try another one.
This way forward?
There's a reaction. Remember what to do here. That's why we gotta practice. You gotta practice. If I tell you once, you're not gonna remember. You have to keep revisiting it. Remember what I said about organic? It can be easy in, but it's also easy out. So what is it? Yes.
We're always right. We're never wrong.
CH2Cl.
Things get all answered.
Like that.
They use words. No, not good, but just saying all.
Good?
Pretty sure that's not how that works.
Let's try again.
Is it one VR?
Mhm.
Yeah, I'm really celebrating.
So, does anybody catch it? Because I was trying to say this. Let's see if we got it.
There's nothing catalyst. So nothing happens.
No reaction.
I wrote the catalyst. Okay, I just got confused.
You made your own catalyst.
I just wrote it in. I wrote it in.
Remember when I give you a mini assessment, it's how I present it to you. You can't just add your own stuff unless I'm asking you for reagent and condition. Uh-huh.
And all of this stuff sample.
Okay, let's try this one. Let's see if this catches you off guard.
You always against this. There's a weird signature.
That's everything, yeah.
Did it fill everything in?
Yep.
There's one of them.
Oh, then it would just call the opposite side. So
Think about it. CH3 directs to the 2, 4, and 6 positions. Look at each CH3 individually. This CH3, if this is carbon 1, it would direct anything being added here, here, and here. The other CH3, when being a director, which I'll use in a different color, blue, when this is carbon 1, you would add to where? This is carbon 1, it's 2, 4, 6. If this is carbon 1, then it's 2, 4, 6, right? What?
This is
Do you see it? So then what are my products? Or what are my potential products, unique products? We know one of them would be to put this. Well, let's evaluate. Are the 3 different from each other? One of them would be to put bless you.
I'll just say.
This is different than that. But what about the third one? Would that be the same as that one? Like to put it here? Aren't these 2 symmetrical this way? So only 2 products here. Make sense? All right. So I wanted you to get familiar with how to do these types of reactions. Now, before we go for the day, I want you to at least take a look at the mechanism. Welcome back. I told you we were going to go till 9:15 today, and we'll stop at that point. So we have time to at least start looking at this mechanism. So we did electrophilic addition earlier today. Now we're going to take a look at something called electrophilic substitution. Just a reminder, for A-level chemistry, there are only 2 new mechanisms. But can any of the 5 from AS show up technically?
Yes.
Yes, which is why you see me reviewing them in the films, because anything from AS chemistry can show up. But there are only 2 new mechanisms. Today and next class, we're going to go over this one fully because this is the big one. I like to call this the big one because on about 9 out of 10 paper 4s, this is the one that shows up. Like, this is the biggest one, so it's the one you really got to nail. It's called electrophilic substitution. Now, you're going to see it says here, because I picked this up from an American resource, electrophilic aromatic substitution, because that's actually how I learned it as well, because it's an aromatic compound that this happens to. But for Cambridge, you only need to call it. So type of reaction for Cambridge is called electrophilic substitution. I actually like adding the word in aromatic because it brings it back to memory. Okay, this happens with A. I had to say with Rick, so I'm not a fan of their terminology. But in this one, but either's fine. If you said electrophilic aromatic substitution, Cambridge would not take it, because if you had correct chemistry, they will give you the mark. Okay, so the general mechanism is always going to be the same. The first step is you are going to have to generate the electrophile. Like, what world is that? Believe me, I know. Meaning you're going to have to come up with an equation that gives you the thing that has the positive charge. And the equations are going to be outlined to you. I'm going to teach you what they are. So this means come up with the equation. Now, once you have the electrophile, you're actually going to follow this process. So this is going to be step 2, which I'll outline as we go through. Your benzene ring, one of the bonds in the benzene ring is actually going to break, which is why you see them right instead of the circle. They see right the 3 double bonds there, but I'm going to show you how Cambridge allows you to write it with the circle instead of with the 3 double bonds. And they grab the electrophile, which is E+. Whenever your substance is positively charged, it's grabbing that. Then you have 4 bonds on one carbon and 3 bonds on another, making a carbocation. And so what happens then is whenever your negatively charged thing is, it grabs the hydrogen, and then that double bond folds back over to restore your benzene ring. So you're going to start with the benzene ring, you're going to end with the benzene ring. But your intermediate, the benzene ring is actually broken. Like one of the double bonds, one of the pi bonds breaks, so it loses its delocalized ability for a little bit. Again, this is an intermediate, meaning does it stay like this? No, this is just like a part of the process. So I'm going to show you once again from scratch how this happens, what bonds break, what new bonds are formed. This same mechanism is going to be for nitrations, for chlorinations, for brominations, and yes, that's their names. Nitration, chlorination, bromination. This is bromination. This is chlorination. If I had NO2, it's called nitration. So those are the fancy names for what we're doing. And so I'm going to use this example to show you what to do from scratch. I'll pause if you needed more time. Are we good? We're good? Okay. I'm going to use this example to show you what to do. It says bromobenzene can be prepared from benzene as shown. And they give you the reaction that we've been learning about. First, name the mechanism. So where would you get the mark if you called it electrophilic? And it's a substitution because remember that a hydrogen is getting out and a bromine is getting in. You're losing one of the hydrogens of the bromine ring and of the benzene ring, you're replacing it with a bromine. So it's electrophilic substitution. I would call it electrophilic substitution, but that's what you're point. Then it says draw the mechanism. So first we're going to talk about generation of the electrophile. So I want you to pay careful attention to what I do here, because this is going to teach you why the catalyst is so important. Without the catalyst, you can't get the electrophile. Maybe I should write that. Without the catalyst, you won't get an electrophile. You won't have an electrophile. And if you don't have an electrophile, you can't do the reaction. So that's why I said you have to have the catalyst, whether it's AlCl3, AlBr3, FeCl3, FeBr3, you have to have that catalyst. And so let's talk about generation of the electrophile. This time, I'm going to show you more information than what's necessary, and then I'm going to show you what Cambridge requires. Because the reason I'm going to show you more information than what's necessary is to understand what's happening. So, Br2, what does its Lewis structure look like? It helps to have Lewis structures because it explains where the electrons are coming and going from. Br2, it's Br, Br, and then you make a what, right? That's right. What's the structure for AlBr3? How many electrons does aluminum have? 3. Did you remember from AS chemistry that aluminum covalently bonds with most nonmetals, and because of its high electronegativity compared to other metals? That's why Al2Cl6 did the dative bond thingy with the 2 arrows. So AlBr3 would be So these two things are what we're going to use to generate the electrophile. Now, I was reading in the textbook and the vocabulary that they use to explain this. They said that the presence of this AlBr3 polarizes this bromine and gives it a dipole. And so you would have one bromine that's partially negatively charged and one bromine that's partially positively charged. And so you get this crazy thing happens. These two electrons from the bromine actually detach and go where do you think? They actually go to fill in the aluminum to make its fourth bond, to give it the octet. So these two electrons from the bromine break. Like this bond breaks. And these two electrons instead go here and take that bromine with it. So your result we would get is this bromine with 6 electrons and this as Al Br, 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 Br. We learned about formal charge last class that I was teaching the class on Thursday. Br is missing an electron, so what charge would this bromine have? Like these two electrons just went there. So this bromine only has 6 instead of 7. What would this bromine's charge be? It lost an electron. What would this bromine's charge be? +1. Does that make sense? And then this aluminum has an extra electron than what it usually has. So what would this be? This would actually be -1. Formal charge proves it. +1, -1. So this is the more than enough information. So I'm going to give you what does Cambridge require you to know. Cambridge requires you to write like this. Cambridge minimum required. Like to get the mark. So for Cambridge, what you would have to do is Br2 plus AlBr3 goes to Br plus AlBr4 minus. If you show this, they give you the point for generation of the electrophile. Does that make sense? It's the same thing? Less writing, but it doesn't show the actual bonds breaking and bonds being formed. So this is what would be worth 1 mark of this mechanism, is generating your electrophile. What's your electrophile here? So this is the electrophile, which is going to get added into the ring. That's the electrophile. You must have that. If you don't have the electrophile, you have no reaction. So the first step that they generally ask for out of these 4 marks is for you to show that electrophile that's being created, which requires the catalyst. No catalyst, no electrophile, no reaction. So now, what do we do from here? How do we actually show this happening? And I'm going to show the minimum Cambridge required. So it's actually really easy to remember, I hope. You would start with the Benzenes ring with a circle plus Br plus. Are you okay with Br plus? From here. So Br plus has how many electrons right now? 6. I'm writing them just as a completionist. You don't have to. You don't have to write the 6. But the reasoning makes sense if you understand. That's 6. And how many does it want? 8. So what happens is 2 of the electrons, and you can just show this from the ring. 2 of the electrons from those delocalized electrons are going to grab this and make a covalent bond. And so you end up with this. And I've looked at a bunch of mark schemes, and you're allowed to write it like this. A broken delocalized ring with a positive charge. And so what you end up with is this. Basically a carbon cation right there. Or you could do it like this. You need to show all of your double bonds. You can also do this. And it would be the same thing if you wrote. And we'll put in bromine here. And this would be great. Yes, this is the intermediate. This is the same thing as that. I want you to pause and see that. The understanding is what I'm waiting for. Does it click? So the two electrons grab the bromine, breaks a bond, grabs the bromine. There's a hydrogen on the same carbon that there's that bromine. So you may want to write that in. The carbon next door is the one that's missing a bond. This also has a hydrogen, but it only has 3 bonds because it doesn't have, one of the bonds is missing. And so now, in the intermediate step, you bring back in your Al, Br4 minus. And what happens is the following. Pay careful attention. 2 of the electrons on a bromine come in and grab, what do you think? They grab a hydrogen. So they grab this hydrogen. That hydrogen cannot be both bonded to bromine and to the ring. So what happens to the 2 electrons that were in the ring, like that were here? They go back into the ring itself, which restores the Benzene ring, like this. You get this, and bromine, AlBr3, and HBr. Because one of the bromines goes with hydrogen, and the other is the AlBr3. So instead of AlBr4 minus, because one of the bromines grabs the hydrogen, it disconnects, and it becomes AlBr3 and HBr. Catalyst is there at the end. Catalyst is there at the beginning. It is defined as a catalyst because it is not consumed in the reaction, it is regenerated in the reaction. We learned that back in kinetics. Start with AlBr3, you end with it. We will practice this again. And if not today, we'll practice this again next class. I think we have time to try it one more time. But they are the same steps every time. All right, so let's try this again. See if we can go through the process. If you need a picture, let me know. We have time to do, it looks like a couple more practice questions. We will not get to nitration today, so unfortunately I will not be able to give you homework. I know you're so sad. We'll be ending by slide 17. You'll get the homework on Friday, along hopefully with the flashcards. Yeah, you need homework. You gotta practice, like this class, you gotta practice. Good to move on? You have to take a picture. Where? This is BR4. Oh yeah, so there's no homework, so you can set for the Olympiad.
Yeah.
So happy for you. Like, is it the first?
I think that's a VR, that's an H.
Test for 2 hours first. And then,
Okay.
Ring ceremony?
Jennifer, our good old like Al.
like, it's like a process. I take a test.
Ready to continue?
I do good on the test. Then I have to do lab.
They're hard. But remember what I told you, start at the back.
Yeah, then take the test tomorrow. You see what it-
All right, let's try this mechanism one more time from scratch with chlorination. Me too. Draw the mechanism of the reaction of chlorine with benzene in the presence of the aluminum chloride catalyst, including generation of the electrophile. Use curly arrows. So, first step, generation of the electrophile. This time, let's give the Cambridge bare minimum for the marks. What do we have to show? It's Cl2 plus AlCl3. And then what you have to recognize is one of the chlorines is moving to the AlCl3, right? So what do you end up with? Chlorine plus AlCl4. But how do the charges work out? Chlorine is positive and AlCl4 is negative. Does that make sense? Yeah? So we identify, we have an electrophile, so now we do the actual mechanism. The electrophilic substitution. You have your benzene ring. Do you want me to do the circle or do you want me to do 3 double bonds this time? Circle. Okay. So if I do the circle, as long as you don't make any mistakes along the way, plus Cl plus. Cl plus means that we're missing 2 valence electrons. So that's bad. So how does it regain its valence electrons? The benzene ring takes 2 of its delocalized electrons and attaches to the fluorine. So you get plus. It's a broken benzene ring. And then chlorine adds, I would add it here because there's also a hydrogen there. And this positive charge means that this carbon here has how many bonds? 1, 2, and 3. Like that's why I'm pointing the positive there. Does that make sense? All I did was add a chlorine and break the double bond. This is not a positive carbon because it has 4 bonds. This one is. So this one's a carbocation. So now what do we do? What's the next step? So we got the AlCl4 minus that has to be brought back in. This chlorine, one of the chlorines from the Cl4, you don't have to draw the whole thing out, but you can if you like. Just one of the chlorines from the AlCl4 is going to grab what? Which one? So one that has the chlorine to make the double bond be able to reform. So it has to be this hydrogen that it grabs. And then these 2 electrons are the one that go back into the ring. And so then your final product here is Cl. And what else? Plus AlCl3 plus HCl. This is the catalyst, just to point it out. This is the byproduct. And this is the major organic.
Where are there 2 H's?
I mean, there's 6 H's.
Oh, you just represent.
I'm just representing what's there so that you can see what's going on with the bonds. Like this has 4 bonds, that was only 3. It has 4 bonds because 1, 2, 3, 4. This has 1, 2, 3. Because that just one through. That's the idea. All right, so we are partially done. Like I mentioned, we were not probably going to be able to finish everything I remember from last year. But I keep the notes always just in case we move forward. But I want you to get practice. That's why I stop and do extra practice questions. So no homework today, but I do have donuts for you. So your donuts are rings like Benzenes. Right?
Benzene donuts.
Benzene donuts.
What do you know about benzene? I don't know about it. This is the whole. Yep.
All right. So
What are you estimating? It's big circle. File. That's the old look.
they look Valentine's-y.
I think you can go. Just I think we can go. No, I think it's.
They can't
You like one?
It'll take the boss. I can have one. Is it even?
Oh, you want me to go?
Because I don't want to touch it.
Okay, because six.
Oh yeah. Yeah.
I want the thing to go on.
Is that the?
The only one too.
I'm just like
Evil.
Like,
You know that's like. Hey, you stole it.
the sweet.
I think.
Guess what?
I think you
I'm
can
pretty sure there's another one. No, maybe.
Yeah, your neck.
You see him there?
What would you like?
not.
Second, your neck.
I haven't.
He really wanted the fucking cream. No, no. I think you should rub it.
Look at it.
So, it is evil. Look, bad things happen to good people. I'm a good person. Bad things. This is.
They're brand new.
You could have seen this coming
Yeah,
and sat there.
these are brand new boxes.
I got
The old
Oh,
ones,
really?
like from
Yeah.
prior years, like that was
But I'm
from,
not
I could blame the middle
I don't
school.
do things.
That was your
I don't
beforehand.
think
It's not about being
That was
evil,
an F
though.
school.
It's about
Yeah, that's what I am. Saying hi. Will you be? That's fine.
I don't know, it looks like cream stuff. Frosting or something?
Best times.
Frosting cream?
Fossil food is.
I don't know what frosting cream is.
And then just gonna ask for a specific. You have another box. Right?
Pick one of these.
because
You know what you did.
You know what you did.
What's is that like foundation?
I don't know, it looks like
Yes.
it looks like frosting. It looks like frosting to me.
It's not like that.
I don't know.
What type is it?
Is it? What is it? I have no idea what that is. Is that like frosted sugar?
I think so.
You say, oh no, my bad. That's-
Yeah.
Okay.
You know you're my enemy now, right?
Wow. The op?
Yes, miss. He's my op now. No,
Thank you.
You're welcome. Well deserved.
So when you did it in the auction basketball.
Oh boy.
Yeah,
That's so dumb.
what do you do?
Just get it like the fanciest one there is left.
yeah, honestly.
Oh, fun.
How does it taste?
He'll eat it.
If you think that feels bad, bro, you don't know what my little brother did to me, bro.
Miss,
Yes,
can I say one for tomorrow? And do you happen to have a Ziploc?
I have Ziploc.
I was thinking burger, right? A smash burger.
And his-
The burger,
Yeah,
got
that's
the little
his
cheese
fault.
on top,
No.
put the
Yes,
lid on,
you-
Yeah.
melted it,
Yeah.
got the caramelized
I'm gonna
on,
call him for his grandma dying.
baked bread a little bit. Sweet and
Same
spicy.
thing.
Burger's burger.
I stand by what I said.
I got the caramelized on,
Because he's at a field.
got a sauce. 3 strips of bacon,
I'll be just.
got it in there, squished it.
He's
I
back.
was ready to go.
I mean, he's able
I'm
to
a-
answer his location actually
I got the
updated.
Coke.
Even
I go.
All right, let me set up for the next
in
class.
my room for 3 seconds.
at the
Go
airport.
get the Coke.
Here.
Come back, and I see the one is moved a little bit.
Or dock or whatever.
I open it up.
Get more bacon.
I hear my stepsister's. I
3,
was like smiling in the hallway, and she's like,
Oh, man.
and I hear my brother.
That's fun.
I open the door, and I kid you know, he's like,
Vincent wanted the bag to say a donut for
that's not being evil, bro. That's like a.
That's like
Bye, kids.
villain.
See?
Oh, I will not go to his funeral. I am telling.
Nah, when was his life? To have someone take away.
He will not be back until
Something they.
I will.
Yeah, but